Hi, my name is Ali Ayub and I'll be presenting our paper Storing Encoded Episodes as Concepts for Continual Learning that is accepted in the ICML workshop for lifelong learning. Humans continue to learn over their lifetime. Machine learning systems, however, require the complete training set to be available in a single batch. In this paper, we deal with the continual learning problem from the class incremental perspective, in which a classification model is supposed to learn from different classes coming in different increments, and its accuracy on all the classes should be competitive. One of the major problems associated with continual learning is catastrophic forgetting, which means a model forgets previously learned classes and the overall classification accuracy decreases. To deal with this, a lot of approaches today store real data of the old classes and use that when learning new classes. However, this leads to a lot of issues. For example, real systems don't have unlimited memory, so storing high-dimensional real data of old classes quickly exhausts their memory. It also leads to privacy and security issues, and it's not biologically inspired. In this paper, we deal with a strict class incremental learning setting in which the model is not allowed to store any of the real samples of the old classes. The solution to that is generative memory using GANs or autoencoders. A lot of approaches today prefer GANs over autoencoders because autoencoders lead to blurry images that hurt classification performance. GANs, however, also lead to issues like generating random images that belong to none of the classes, which also hurt classification performance. So in this paper, we use autoencoders to generate old class data. But to deal with the blurriness problem, we use the content loss from the neural style transfer algorithm. In particular, we use the classifier model that is being trained on all the classes so far and pass the real image and the reconstructed image from that to get the convolutional features. And an L2 loss between these convolutional features is used as the content loss. The autoencoder is trained on the combination of the reconstruction and the content loss. After autoencoder training, we pass all the real images from the encoder to get the feature embeddings, which are stored to be later used to create data for the old classes. These feature embeddings are called encoded episodes because they're inspired by the hippocampal encoding process. When the system runs out of memory, we use an idea from the neocortical memory integration process, in which we keep combining encoded episodes to generate centroids and covariance matrices and remove the encoded episodes themselves. And we keep doing this process until the memory budget is reached. So the classifier model is trained on three streams. First are the real images of the current increment. Second, we pass the encoded episodes of the previous classes through the decoder to generate reconstructed images. Lastly, we sample the centroids and covariance matrices of the old classes in the form of a Gaussian distribution to generate pseudo-encoded episodes, which are passed through the decoder to generate pseudo-images. Now, the reconstructed and pseudo-images could look still very different from the original images, which can hurt classification performance. Now, to deal with this, during classifier training, we reduce the effect of the reconstructed and pseudo images by weighting down their cross entropy loss term. The overall classification loss then is the cross entropy loss of the current increment, the weighted cross entropy loss for the reconstructed images, and the weighted cross entropy loss for the pseudo images of the old classes. So for the evaluation of our approach, we tested on benchmark datasets and compare against state-of-the-art methods that use generative memory and the one that use real data of the old classes. First, we tested on MNIST. That is one of the famous datasets for testing the continual learning approaches. But we see that our approach produces very similar accuracy to some of the other generative memory approaches and the batch learning upper bound, which shows that the dataset might be too simple for testing continual learning approaches. Because of this, we test our approach on ImageNet 50 dataset, which is a smaller subset of the ImageNet dataset. For this approach, only DGMW reported results among the generative memory approaches. But we see that our approach beats DGMW with significant margins. And our approach even beats other approaches that use real data of the old classes like ICARL or EIL, which shows that our approach is actually able to produce good results on simple or complex datasets. Here are some of the reconstructed images by EEC, and you can see that there is no blurriness problem. So the memory usage analysis of our approach on ImageNet 50 dataset shows that it uses about 51% lesser memory than DGMW. That's the current state-of-the-art method among the generative memory approaches. Now to test the effect of memory integration, we allow the model to store only 5,000 samples, which means that the total number of encoded episodes, centroids, and covariance matrices can only be 5,000. Even in this case, our model achieves 13% higher accuracy than DGMW, even though it uses about 78% lower memory than that method, which kind of shows that our approach deals with the two main issues of continual learning: catastrophic forgetting and the memory storage issues. Thank you.